Okay, let's start. So, hello, my name is Youngjun Kim. I'm a professor of physics here at the University of Toronto, working on experimental condensed matter physics. It is my pleasure to introduce you today's speaker, our Welsh lecturer, our Professor Pablo Carrillo Herrero. Pardon my pronunciation. Um, and uh, and Professor Harilio Herrero is not actually a stranger to our department. So he actually mentioned yesterday that he's been coming to Canada as a member of the C4. But actually, he was here. If you are here, if we were here before, like 12 years ago, I think he visited here and then gave a physics colloquium in our usual physics 102 in MP building. As a young up and rising faculty member at MIT at the time, now he came back as a distinguished world-renowned researcher who's going to deliver, who has already delivered the first Welsh lecture, and then he will deliver the second part today. So Professor Herrero is currently Cecil and Ida Green Professor of Physics at MIT, and he's from Spain, but he did his PhD in physics from Delft University of Technology in the Netherlands. And after his postdoc at Columbia, he has been at MIT since 2008. He has won numerous awards. Obviously, I don't have time to list all of them. I mean, some of the notable ones are the American Physical Society's 2020 Oliver E. Buckley Prize in condensed matter physics, and also the 2020 Wolf Prize in physics. And he's also a member of U.S. National Academy of Sciences and also a Spanish Royal Academy of Sciences. So, and it is not surprising that there's a good turnout here, because yesterday Professor Harillo Herrero actually gave ample advertisement for today's lecture. It's going to be a very, very interesting thing. So I'm very much looking forward to today's lecture. So let's welcome Professor Harillo Herrero.
Thank you very much. Again, it's a great pleasure to be here. I wasn't sure how much overlap was there going to be between the two audiences, so I'm not going to assume that anyone was here yesterday, right? So plenty of what I will say will be familiar from yesterday, but there will be also some new elements, okay? And given that yesterday the students showed that they had been highly trained, I will try to even write down one equation or two, see how it goes. So again, since I shouldn't assume that anyone was here yesterday, it's a great pleasure to be in Canada, at the University of Toronto. As it was mentioned, I have been coming to Canada for now 5 years. I've been a member of CIFA, and I had been earlier in Canada, but now I come regularly to Canada all the time, and I really enjoy this fantastic country, lots of friends, beautiful cities, so very happy to be here. I want to tell you about the magic of molecular quantum matter, and the word magic is very clear, again, assuming that you will hear yesterday where it comes from. But I will explain, each of the terms that come into the title of this talk. But I want to start with something which is, from a bit more general point of view, from the concept of emergence, and emergent behavior of quantum matter. Yeah? And this is related to the fact that, when you look at physics in general, not just condensed matter physics, but if you take, the behavior of you try to understand the behavior of a single particle, for example, a single electron spin, this is something that within quantum mechanics we understand quite well. Right? It's, the behavior of a single particle is simple, and what I mean by simple is we understand it. Okay? We can describe it mathematically. However, when it comes to multiple particles that interact strongly with each other, okay, that behavior is much, much, much harder, exponentially harder to deal with. And as a result, the behavior of many interacting particles is difficult and not understood. Okay? We don't have nowadays the computational capability to understand the properties of many interacting particles beyond maybe half a dozen or a dozen particles. However, many of the most fascinating states of matter that occur in the universe are related to that behavior of many strong interacting particles. This is something that happens not just in condensed matter physics, but in all areas of physics. For example, a few hundreds of nanoseconds after the Big Bang, you get this state called the quark-gluon plasma, where quark and gluons are very strongly interacting. There are many particles there interacting strongly with each other. In neutron stars, which happen after supernovae explosion, the different phases of neutron, the different phases of nuclear matter in neutron stars, okay? Many phases, and they are all very strongly interacting and very difficult to describe. And then, for example, closer to condensed matter physics, if you take a system of two-dimensional electrons in a magnetic field, they enter this regime called the fractional quantum Hall regime, okay? Where electrons acquire very interesting topological and they become entangled in very interesting ways. For example, the quasi-particles in this regime acquire fractional statistics and fractional of a charge, for example. If we zoom in a bit, now closer to condensed matter physics, following the fractional quantum Hall effect, in general, the field of strongly correlated quantum materials, this includes hundreds of materials, many families, classes of materials where the electrons interact very strongly with each other. And this is a picture of one of the most famous members of this strongly correlated quantum materials family, is the high temperature cuprate superconductor, floating in this, at low temperatures. In the phase diagram of temperature versus doping, charge density, these high temperature superconductors exhibit a number of phases in this mode, antiferromagnetic, strange metals, silicate, with superconductivity. Plenty of these phases, we have a very poor understanding of them, okay, to this day, despite, 4 decades of research, intensive research into this system. Let me give you a little bit more insight into some of this. So in the high temperature cuprate superconductors, all of the action takes place in these copper-oxygen planes. These are two-dimensional planes of alternating copper and oxygen atoms. Yeah? And if you grow the stoichiometric compound of a high temperature superconductor, you have 1 electron per copper atom. Yeah? Now, in each of those copper atoms, you can put 2 electrons, but since we have placed only 1 electron, it should be very simple for electrons to just jump from copper atom to copper atom and conduct electricity. This should be a good metal in single particle physics. However, what happens in this material is that there is a very strong repulsion between electrons, so that double occupancy of a copper atom by 2 electrons is heavily penalized. And as a result, when you grow this stoichiometric compound, you form something known as a correlated Mott insulator, where the electrons get stuck in their positions, and they cannot jump from atom to atom because of a strong Coulomb repulsion between the electrons. Now, something very interesting happens if you remove a few of those electrons, right? Or you dope the system with holes. Removing a few electrons is like adding holes, we call it. So if you remove a few of these electrons, now there's some empty sites on your copper oxide plane, so that the electrons now don't have to repel, they are not repelled by an existing electron there, so they can jump. So there is this correlated dance of electrons where, you jump between empty and occupied sites like this, okay? And this happens in such a way that almost, magically gives rise to high temperature superconductivity. Okay? Now, we believe that the simplest model that describes this type of behavior is, given, by the Hubbard model, in honor of John Hubbard, where there are only 2 parameters in the system. The penalty U, the energy penalty U to doubly occupy, a site, and the hopping energy, the kinetic energy, hopping energy T between an occupied and an empty site. And despite the apparent simplicity of this model, these 2 parameters, and you have a whole bunch of electrons in this lattice, we do not know how to solve it exactly, okay, theoretically. And as a result, I mentioned, the word that I use is we believe that this model describes this phase diagram, and I use believe rather than we know, because again, we cannot theoretically solve it. And there is no direct mapping that all theories agree, between this type of model and the phase diagram that is experimentally observed. Yeah? And this is despite, many decades of intensive, experimental and theoretical research. Now, this difficulty of solving the problem of strongly interacting quantum matter has led to alternative platforms to try to investigate correlated and topological physics. And this, one of the most famous and novel approaches is that of using ultra cold atoms in optical lattices to investigate strongly correlated matter. Right? So what the community of ultra cold atoms has done over the past 20 years or so is the following, they can shine lasers at each other. Okay, they form an interference pattern there, and you have a periodic potential, and you can load that periodic potential with atoms. And then the cold atom community has this tuning knob, it's called a flashback resonator, it doesn't matter what it's called. They have essentially control over the strength of the interactions between those atoms. And as a result, already, a bit over 20 years ago, they were able to demonstrate a transition between a superfluid and a multi-insulator by changing the strength of those interactions. Okay? Now, this was done with atoms which had an integer spin. So these were bosonic atoms, and this was a realization of what is known as the Bose-Hubbard model. A few years later, the community was able to do this with atoms with half integer spin, fermions. So this was a Fermi-Hubbard model that's a step closer to electrons, because they have fermions. And just to give you an idea of some of what the community has been doing recently, they have been able to realize antiferromagnetism in the Fermi-Hubbard model. So they use they can load these atoms into this array, and then they're able to image locally the spin of the electrons, and they can see that it alternates up, down, up, down, up, down. So they are, starting to explore this phase, of the phase diagram, antiferromagnetism, multi-insulator, etc. Now, they would like to explore the entire phase diagram, and in particular, try to reach this region of D-wave superconductivity with the D-wave superfluidity due to repulsive interactions in the cold atoms case. However, one big technical challenge that the cold atoms community has is that they're currently working in the very high temperature regime. Now, I say high temperature, in reality, they're working at about a nanokelvin, okay? But that is high temperature for cold atoms and the energy scales of the system. So they would like to cool down. So they're in this area. They would like to cool down to see this, but they have to cool down about 1 to 2 orders of magnitude, they believe, in order to reach this region. And this is something which, there's no fundamental law of physics preventing this from happening, but it's technically extremely challenging. Right? And as a result, although there have been steady progress, it's not as fast as they would like, and they have been able to observe less phases of quantum matter than they would have liked because they are in this high temperature regime. So we have traditionally these two platforms to study strongly correlated physics and topological physics. One is just usual quantum materials that we've been exploring for 100 years or so, where the lattice scale is over the order of a few angstroms. Okay, this is a picture of high temperature Cooper superconductor, for example. Here we have thousands of these materials. Okay, but if you take just a particular crystal, you have relatively little control over the properties of that crystal in terms of changing its behavior. If you want to have a different behavior, typically you have to grow a different crystal with a different chemical composition, with a different disorder realization, etc. Here with the cold atoms, where now this time the length scale is about a micron, the wavelength of light. Here we have exquisite control over all the parameters of the system. So we can do experiments just in a single, platform, in a single, lattice. However, because of this high temperature limit, the number of phases of quantum matter that have been observed has been limited, so far. And what I want to show you and tell you about today is about this new platform, Moiré quantum matter, which is complementary to these two other platforms. It's also complementary in terms of length scales. The Moiré wavelength, the Moiré length is of order 10 nanometers. Okay? So it's a factor of 100, from either of these other two platforms. These length scales, with the length scales come, different energy scales. In traditional quantum materials, typical temperature scales for various parameters of the system can vary between 100 and 1,000 Kelvin or so, maybe 10 to 10,000, depends on the material. For cold atoms, we're talking about nanokelvin energy scales. For Moiré quantum matter, the energy scales are of order 1 to 100 Kelvin. And that is actually a relatively convenient energy scale to explore in a solid-state physics laboratory. Now, initially, the thing that enabled this Moray quantum platform was something which has come to be known as twistronics, which is that the fact that with the advent of 2D materials, we have been able to do something which was unprecedented in the history of material science. We're able to choose the relative twist angle or the relative angle between crystalline planes in structures. So we can do, for example, we can take a graphene sheet, put another graphene sheet on top, and we can put it on top with any angle of rotation, any relative angle or twist angle between the two crystalline planes that we choose. Yeah? We can do 30 degrees, 37 degrees, 1.1 degrees, while not, as I will show, any angle that we want. When you put these two periodic structures with an angle between them, you create a super periodic structure, okay? Or nearly periodic super periodic structure, a Moray pattern, and hence the name Moray quantum matter. Now, these are these Moray, some of you may have been here. I'm going to pass them around again. Okay, if you already play with it, please pass it around. And this gives you an idea of how this Moray wavelength and these Moray patterns change with the angle between the two lattices. Now, the magic of this Moray quantum matter platform is that within the span of a few years, we have been able to realize pretty much all of the phases of quantum matter known, from exotic type of correlated insulators to exotic unconventional superconductors, many topological phases, many new types of magnets, more exotic crystals, new types of ferroelectrics, strange metals, generalized Wigner crystals, excitonic insulators, pneumatic systems, et cetera, et cetera, et cetera. You name it. You give me a phase of quantum matter, we've pretty much done it, okay? And in fact, we have also discovered new phases of quantum matter that didn't exist before using this platform, okay? And it has all occurred relatively quickly, just within the past 6-7 years. So with this introduction, this is what I want to tell you about today. I'm going to tell you about graphene and magic angle graphene. We're going to go a little bit deeper than what we saw yesterday. Yeah? Then I'll tell you about the rise of Moray quantum matter. This is something that I largely mentioned yesterday, but I'll go a bit more in depth on some of the techniques and some of the discoveries that were done. And then I'll tell you, a lot of this work has been focused on graphene-based systems, but this actually is something that happens for many other 2D materials. So I will tell you today about Moray magic beyond graphene, in particular Moray ferroelectricity in Valley boron nitride. And then I'll end with an outlook, which is very similar to the outlook that I mentioned yesterday. Okay, so graphene. Graphene is a honeycomb of carbon atoms. And so all of these atoms in these hexagons, they're all carbon. They are, from the chemical point of view, identical, carbon. However, from the crystallographic point of view, they're different. Okay? We have two types of atoms, the A and B sublattice, or the red and green balls in this honeycomb. Okay? That is because in order to tile a honeycomb, you need 2 unit vectors and a 2-atom basis. Okay? You cannot do this just with a single atom and lattice vectors. Now, it is very simple to calculate the electronic properties using quantum mechanics, a simple quantum mechanical model, the electronic properties, the electronic structure, or the energy momentum dispersion, okay, of electrons in graphene. This is energy versus momentum in the X and in the Y direction. Okay? And it's a very unusual type of electronic dispersion. I mentioned this yesterday in a simpler context. If you zoom in near the Fermi energy, the relationship between energy and momentum is linear. Okay? That's very odd. Usually, the relationship between energy and momentum in solids is quadratic. The kinetic energy goes as P squared over 2m, okay? Or 1/2 mv squared, the typical kinetic energy, classical physics. However, for electrons in graphene, you have this linear energy momentum dispersion. That looks more like the energy momentum dispersion of photons of light, okay? The usual cones that you see of light, when you think about Einstein and so on. Graphene is a zero-gap semi-metal, linear energy momentum dispersion. Now, obviously, electrons are not photons, okay? So if you look at what is the equation that governs at low energies, the behavior of electrons in graphene happens to be nothing else but the Dirac equation in 2 dimensions for massless particles. So this is the equation that governs the behavior of ultra-relativistic massless particles. Yeah? Now, this is, don't get too worried. This is about the only equation I will show, okay? So, in the usual Dirac equation, energy, you can see energy is linear in momentum here. And in the usual Dirac equation, this is a spinor that tells you whether the electron spin is up or down. Here, this is actually a pseudo spinor which is telling us whether the weight of the electron wave function is on the A type of atom or on the B type of atom, okay? The only other thing that I want you to remember about this dispersion and electrons in graphene is that we have two of these double cones, which are called valleys, the K and the K prime valley. So we say that electrons in graphene have this fourfold degeneracy. Electron can have spin up, spin down, or they can be in valley K or in valley K prime. Okay? Just remember number 4. It will appear later. Okay? That's all I want you to remember. Okay, so this is a single sheet of graphene. What happens if you put 2 sheets of graphene on top of each other and you rotate them? A moire pattern forms where the moire wavelength, the length, the distance between the soccer balls that you see in the screen, is roughly inversely proportional to the twist angle, at least at small twist angles. Yeah? Because these 2 lattices are identical, this can go all the way to infinity. If these 2 lattices, were 2 different materials with slightly different lattice constants, there will be a saturation of it will be a maximum moire wavelength, even if you perfectly align them. Yeah? But for graphene and graphene, it can go all the way to infinity. Let me stop this before you get too dizzy. And so let's see now, that was what happens in real space for graphene on top of graphene. Yeah? Let's look now at what happens in reciprocal or momentum space, and therefore what happens to the electronic structure. So if you have a single sheet of graphene, this is the electronic structure, Dirac cones. We have the K and K prime valleys. This is the Brillouin zone and the reciprocal lattice. And if you have some finite Fermi energy, so that you're cutting your Dirac cone at some finite height, you have these Fermi disks here, okay? KK prime. Only 2 of them are independent. The other are just copies by reciprocal space, lattice vectors. So this is what happens for one graphene sheet. If I place now another graphene sheet perfectly aligned to it, yeah, then the reciprocal spaces are on top of each other, okay, in momentum space, perfectly overlapped. What happens now if I rotate in real space? Well, the reciprocal spaces also rotate, and they rotate by the same angle, okay? So rotation leads to a separation, in particular, of these Dirac cones. Okay? So twisting leads to layered Dirac cones separating in momentum space. And they separate by a distance in momentum, which is proportional to the sine of half the twist angle. So if you rotate by a small angle, by a small theta, this is a rotation, separation, which is proportional to the twist angle. Okay? So let's start from a small angle, a small rotation, but not ultra small, but small angle. And then let's continue rotating towards smaller and smaller angles and see what happens. So this is what I showed yesterday, okay? You have the 2 Dirac cones, which are spaced by some amount proportional to the twist angle. This is the Dirac cone of layer 1 of graphene. This is the Dirac cone of layer 2 of graphene. This is for a particular K valley, okay? And then you can see that this would be the situation that would occur if electrons in one graphene sheet did not know, they weren't aware that there is another graphene sheet. Yeah? Like this would, for example, would happen if graphene sheets were very separated. But because when we place graphene on top of graphene to make twisted valley graphene, the 2 graphene sheets are just spaced by a few angstroms. Electrons are very much aware that the other graphene sheet exists, and particularly they can tunnel between the 2 graphene sheets. Okay? That interlayer tunneling gives rise to a energy repulsion here at that crossing points, band repulsion. Okay? This is the same thing as bonding, anti-bonding states in a hydrogen molecule, except that this is bonding, anti-bonding bands in a giant twisted valley graphene molecule. Okay? So the situation that I depicted here is when this 2W is smaller than the energy of that crossing point, okay? Which is decay. If we decrease the twist angle, yeah, we make those 2 Dirac cones get closer and closer and closer to each other. And therefore, at this crossing point of the Dirac cones, the band repulsion gets them towards lower and lower and lower and lower energy, the closer they get. Yeah? And as a result, as we decrease the twist angle, there is some angle for which this lower band that has this push down in energy gets pushed down all the way to 0. Right? When that happens, we say that a flat band condition has been realized or has been reached. Yeah? And the angle corresponding to that flat band condition is the magic angle. It was coined magic angle by Bistritzer and McDonald. And that happens to be 1.1 degrees for graphene on top of graphene. Okay, and again, it depends on the value of that interlayer handling. Yeah? I will mention how this can be varied later. I should mention that there was, at about the same time, other theoretical work by Suarez Morel and collaborators, and also experimental work by the group of Eva and Ray, where they used a scanning tunneling microscope. There, I won't describe the details, but basically these features here, where that band repulsion takes place, gives you a peak. For the experts, it's called von Hoff singularity. So it's a peak in the density of states that can be picked up by the scanning tunneling microscopy. And this group showed that that peak was going to low energies, and extrapolated to zero at about 1.1 degree. So this behavior, which is all single particle physics behavior, was relatively understood, or more or less understood, about 15 years ago. Okay. The thing that came later was the many body physics that I mentioned at the beginning. That I will tell you about. So now this is a cartoon. Okay. This is an actual calculation of the electronic structure of magic angle twisted bilayer graphene, energy versus momentum. These are the flat band are called, okay? These bands that happen, when you reach the flat band condition. They're not perfectly flat, okay, mathematically flat. There is a little bit of dispersion, but it's orders of magnitude, less dispersive than for the original graphene dispersion. Okay? In fact, these are the flat bands. These are the first Moiré mini bands. There are many such bands which come from the folding of the Brillouin zone, when you do this superperiodic modulation. And these other Moiré bands have a much higher dispersion, getting closer to that of the graphene, original graphene dispersion. Now, if we place electrons in these flat bands, okay, where do they like to go in terms of real space? So in order to go from momentum space to real space, you have to do a Fourier transform. Okay? And the Fourier transform of a very flat object is a highly picked object. So if you look at where the electrons that sit in this flat band, where do they like to be? They like to sit in certain regions of your Moiré pattern. Yeah? And in particular, they like to sit in regions which we call of AA stacking, where locally it looks like all of the carbon atoms in layer 1 are underneath the layer, the carbon atoms in layer 2 directly underneath. Yeah? Now, in reality, there's a small twist angle. So if you walk a few nanometers, that small twist angle leads to this out of registry such that there are regions which we call of AB and BA stacking that separate those regions of AA stacking where the electrons like to be. So from the point of view schematically, magic angle twisted bilayer graphene looks like this. There are these regions of AA stacking where the electrons like to be. And then there are these regions of AB and BA stacking where the electrons do not like to be. In a slightly more realistic schematic, this is what magic angle twisted bilayer graphene looks like. There are these regions of AA stacking that I shaded in yellow, where the electrons like to be, and then the regions of AB and BA stacking where the electrons do not like to be. This is going to be sort of an analog of a triangular Fermi-Hubbard lattice of the cold atom type. Okay? Where we're going to place our electrons in certain sites and control them and so on. However, the analogy only goes so far. I use quotes many times here because, first of all, it's not really triangular. This is actually a honeycomb Moiré lattice because the AB and the BA regions are not identical. Yeah? It's also not a standard Fermi-Hubbard lattice, because this electronic structure of magic angle twisted bilayer graphene has certain topological properties that prevent a direct mapping to the usual vanilla Fermi-Hubbard lattice that people use in cold atoms experiments. So there, this is sort of an analog, but it's actually quite a bit different in practice. Okay, so how do we make, before I start showing you some data, how do we make these devices? Okay, explain this again. Just a bit, let me show you to you again. So we start with a glass slide, a transparent glass slide, which has a polymer sequence here, and then at the bottom there is a sticky polymer. Okay. Then we bring a substrate which has a hexagonal boron nitride flake on it. For the purpose of the first half of this talk, boron nitride is just a high quality dielectric, insulator that does nothing. It just helps maintain the pristine properties of graphene. We'll see in the second half that you can do a lot of stuff with boron nitride, okay? But for the first half, this is just an inert high quality substrate. maybe something like 10 nanometers thick or so. So we come with a sticky polymer and we pick up the boron nitride substrate. Then we bring a different substrate with a graphene sheet on top of it. And we position our hexagonal boron nitride sort of halfway on top of this graphene sheet. And then we come and we tear half of the graphene. Okay? Now, from the top view, what we have is the substrate with half of the graphene, and then the glass slide with the polymer stack with the hexagonal boron nitride and the other half of the graphene. These two graphene sheets are at different height, but the position and orientation of their atoms, carbon atoms in both sheets, is correlated because they came from the same crystal. Okay? So what we can do now is we can rotate our substrate by any angle that we want, for example, 1.1 degrees. And then we can translate this on top, and then we stack it. Yeah? And we pick up the second half, the other half of the graphene. Amazingly, this produces this, very, fine, very precise Morley pattern at 1.1 degrees that now the electrons are going to experience the strength of that Morley potential. Yeah? And then you can continue doing fabrication, in the standard way that we do with graphene devices. Now, I mentioned this tear and stacking. Nowadays, we actually use a little bit slightly different techniques. We can laser cut rather than tear, which is a pretty violent thing. All of you that have taken plastic wrap and you have torn it, you see what happens at the edges of the, the thing gets sticky, falls, wrinkles, It's easier to just laser cut it or use an atomic force microscope to cut it. So techniques have improved, but this is the basics of how this thing gets done. Okay, so then we do standard nanofabrication that thousands of groups around the world can do. Where we take the twisted bilayer graphene, it is encapsulated in top and bottom boron nitride, so that we have a nice sandwich there with the cheese is the twisted bilayer graphene, and its properties can be maintained, very pristine. We contact with source and drain electrodes so that we can apply a voltage and measure a current that circulates through this device. And importantly, we have also a metallic electrode called a gate electrode. This one forms a parallel plate capacitor with the twisted bilayer graphene. So if we apply a voltage, which we call a gate voltage, to the parallel plate capacitor, we can vary the charge density in both plates of the capacitor, in particular on the twisted bilayer graphene. Okay, so this is a geometry, which is a field effect transistor geometry, for those of you that know, a bit more engineering or what an FET is. Okay. So before I show you data on magic angle twisted bilayer graphene, let me show you what happens when you measure just a regular graphene field effect transistor. Yeah? So if you measure the conductivity of just one layer of graphene versus charge density, yeah, you have this V-shaped conductivity. If your Fermi energy is deep here in your valence band, you have lots of holes, so your graphene conducts very well. If your Fermi energy is deep into your conduction band, you have lots of electrons, so your graphene conducts very well. If your Fermi energy is near the Dirac point, where there are very few carriers, your graphene conducts poorly. So the conductivity of graphene versus charge density is this V-shape, that has been measured by thousands and thousands of groups all around the world. Let me show you what happens if you have magic angle twisted bilayer graphene. This is the conductance, versus charge density, actual data for a magic angle twisted bilayer graphene device. You can see that near charge neutrality, I have this V-shape. The system sort of remembers it's made of graphene, okay? But then you have all this up and down, kind of crazy. So what is all that? Yeah? So to understand this, let me go back to this diagram, to the electronic structure. Yeah? And remember number 4. I told you it would appear again. Yeah? So if we start from zero energy, from what we call the charge neutrality point, if I remove 4 electrons, or equivalently, I add 4 holes per Morey unit cell, my chemical potential goes from 0 all the way here to the middle of this single particle band gap. As a result, because now my chemical potential is in the middle of a band gap, I don't have available states to conduct electricity for my electrons, and I get an insulator. So when I put 4 holes per Morey unit cell, I get a single particle insulator. This is behavior that it's easy to understand in single particle physics, okay? I have a band gap, therefore I cannot conduct electricity. The system turns into an insulator. If I go from 0 all the way up, I feel then 4 electrons per molar unit cell. Again, this number 4 has to do with this spin body thing that I mentioned earlier. So if I put 4 electrons per molar unit cell, I have my chemical potential in the middle of this band gap, and therefore I have a single particle insulating behavior. That behavior is easy to understand. It was predicted. And in reality, interactions modify this thing, but to 0th order, this is quite simple to understand. Now, the surprise came when we did the following. If you place 2 holes per molar unit cell or 2 electrons per molar unit cell, now my chemical potential is in the, in a region, somewhere in this flat band with a very high density of states. This should be a very good metal and it should conduct electricity very well. However, the conductance is 0. What has happened here is that a correlated insulator, an insulating state due to interactions between electrons and holes in the system, okay, has appeared, okay? So this was the first surprise, okay, that we found. How come that this system becomes an insulator when it should be a very good metal? It has to do again with this correlated insulating behavior. Now, the other thing that we saw is these measurements, they were 2 terminal measurements, which means the following. I have a source and a drain and apply a voltage and I measure a current. Yeah? This is a geometry which is convenient to use if you are looking for insulators. We were in fact looking for insulators. Because if you have a series resistance from your contacts or other stuff, it doesn't matter because you expect to measure infinite resistance. Who cares if there's an additional extra resistance? Yeah? But what happened with my students, I don't have the temperature dependent data here, but let me tell you what happened is that this was measured at 300 millikelvin. What happened is that next to this insulating behavior, there was this peak in conductance. And this peak, if you increase the temperature, decreases. If you decrease temperature, it increases, okay? So my students and I, we were like, this is kind of funny. This thing, it seems like it wants to conduct very well when you lower the temperature. Wouldn't it be crazy if this thing turned out to be a superconductor, But it was like, there was 0 predictions. No one ever imagined. We were almost joking, like, yeah, can you imagine this could be this? So at some point we were, joking, could it be? And my student looks at me, should we make 4 terminal devices? These are devices where now you're able to measure, apply a current and measure the voltage bias and get rid of any series resistance. So if you want to see if something has truly 0 resistance, that's the geometry you have to use. So my student looks at me and says, should we make 4 terminal devices? And I said, of course, I think this is crazy, most likely not going to work, but let's make 4 terminal devices just in case. And well, just in case turned out to be, true, and we discovered superconductivity in this system. So when you dope a little bit away from the correlated insulator, you have an electrically tunable superconductor, okay? By the way, I should mention that this behavior, correlated insulator and the superconductivity, only happen in a relatively narrow twist angle range around 1.1 degrees, roughly between 1 and 1.2 degrees, which tells you that this is related to that, establishing that flat band condition, yeah? So when my students showed me this data, and we have, different devices, and by now we have many, many, many devices, when the students showed me this data, it immediately reminded me of the hundreds of times I had seen in seminars this type of phase diagram, okay, which I showed a bit earlier too, okay? Let me flip this axis so that the electron and hole doping correspond to exactly the way we have them. Here we are. In the high temperature, this is the phase diagram of the high temperature couplet superconductor family. Yeah? Temperature versus doping. Doping is the same thing as density, okay? 0 doping here actually means 1 electron per copper atom, okay? So they count doping as deviations from 1, okay? Or extra electrons or holes. So 0 means 1 electron per copper atom. That is a mode insulator. If you dope with holes, you get superconductivity. You dope with electrons, you get superconductivity. Here at, this doping of 2 electrons or 2 holes, we have an extra factor of 2 because of that value thing, remember? you get a correlative insulator. If you dope with holes, you have superconductor, electrically tunable superconductor, you dope with electrons the same. Now, despite some similarities between these two things, I should point out that this is actually quite a bit different, okay? There are many differences, this is a hexagonal lattice, this is a square lattice, and the energy scales are different, etc. But one important difference also is the fact that this is a theoretical phase diagram. Okay? In order to populate this with experimental data points, you have to grow hundreds of crystals with different chemical compositions, with different disorder realizations, usually using different materials types, because you cannot dope with electrons and holes over the entire range using the same type of material. This is done all in a single sample with a single disorder realization without chemical impurities. And we go from here to here, dial in a voltage knob, which takes a few seconds, okay? So obviously this is something that, that is quite advantageous for many things. Now, let me tell you a little bit about what happened after this, okay? So, we posted this in March of 2018 to coincide with the March meeting of the American Physical Society. And then what I call the theory tsunami came, okay? You experienced a tsunami yesterday, some of you, which is, this is just a list of the papers that appear within the first weeks, of us posting our paper in the archive. This list has now many thousands of papers, okay? And people wanted to know what is the origin of the correlative insulator states and what is the superconducting order parameter, okay? So I already made a joke yesterday about this angle of correlation. So let me, tell you about a different anecdote about this list. So the first paper was by Senke Xu and Leon Valens from University of California, Santa Barbara, a paper telling us that it should be D plus ID chiral topological superconductor. Okay? Then there were hundreds of other papers with all other letters of the alphabet here for the order parameter. Let me tell you about the second paper. So the second paper was by Bolovic, famous condensed matter theorist, in Finland, working in Finland, where he said, he sent us an email and said, Pablo, finally you have experimentally realized everything I predicted, switch, that was not a surprise because we got many emails like that, I predicted everything myself before, But in the case of, which of course, okay. But in the case of Bolovic, I opened, the paper. He posted the paper, where he said, look, I already told you in 2013, and I went to 2013, and indeed, he had already told us the following. He said, for decades, many decades, going back to the 60s, so 1960s, there have been all these strange reports of superconductivity, in some cases, room temperature superconductivity in graphite. It cannot be that so many people are wrong. So there must be some truth to this, okay? Even though no one could reproduce each other, it was always very weird type of experiments. Like I said, let me tell you, I've solved the conundrum, how come that all of this mess, what's happened? All of these experiments where people have measured superconductivity or room temperature superconductivity in graphite have this common factor, that they are made in graphitic samples, which are called turbostratic graphite, where there are small misalignments between the graphene planes in the graphite. Okay? So this is in 2013. Then what happens is, if you have this turbostratic graphite, you're going to have flat bands, remember flat bands were already known, and you're going to have effectively high temperature superconductivity from very strong correlations in these flat bands. Yeah? So this is something that, and then, so that was in 2013. And then in this paper, which was just posted a week or two after we posted our results, he said, finally, someone has done the control experiment. Just take two layers, make a small angle between them, make flat bands, and you see superconductivity. So now, come on, just stack a few more layers and get to room temperature, So this is what, he told us, that we should do, So again, I used to think, I was vaguely aware of those graphite superconductivity experiments. They're again very weird, not reproduced and so on. I used to think they were, maybe crazy or whatever. Now I'm like, who knows? Maybe there's something there. Okay, but there was an interesting anecdote about Bolovic. I'm going to be in Finland next year. I'm looking forward to meeting him and see what he says. Yeah. So anyway, so rather than tell you about all the ways in which theories have predicted things and are they right or wrong or contradict each other, etc., let me tell you about something about what has happened experimentally, which I mentioned yesterday, but now I'm going to go in a bit more detail in some of the cases. So the first thing that has happened experimentally, that happened experimentally, is that we were able to reproduce ourselves. That doesn't always happen, that you're able to reproduce yourself. It's very good when it happens, so that's great. But much more important than you reproducing yourself, which is of course essential, is when other groups reproduce your own results independently. Only then it becomes real science, real physics, okay? And thankfully for us, many, many, many groups have reproduced our results and extended them to very interesting systems. The first two groups to reproduce our results were these. The first was a collaboration between the group of Corey Dean at Columbia University and Roy Young at the University of California, Santa Barbara. They did a very nice experiment. First, they made a sample at magic angle, 1.1 degrees, and they saw correlated insulators and superconductivity, the exact same thing that we saw. Then they made another device at a larger angle. You can see here, 1.27 degrees. They measured it, and they did not see correlated insulators and superconductivity. But then they did something very clever, which is they applied hydrostatic pressure to the two sheets. When you apply pressure, you get those graphene sheets closer, so the interlayer tunneling increases, so the magic angle condition changes. It's no longer at 1.1 degrees, but it goes to a higher angle, okay? Because you get closer to that flat band condition, at a larger angle. And together with collaborators from Harvard, we have predicted theoretically what would be the magic angle condition as a function of pressure. Yeah? So they knew exactly which pressure they had to dial to in order to get the flat band condition. And when they measured the devices at that high pressure of 1.33 gigapascals in this case, they were able to measure correlated insulators and superconductivity. Okay, so this was something really very nice experiment, very nice demonstration that it is that flat band condition which enables you to measure this strongly correlated physics. The second group to reproduce our results, a little bit later, was group of Dimitri Efetov, back then at ICFO in Spain, where they measured additional superconducting domes. By now, over a dozen groups, have, reproduced and extended, these robust superconductivity measurements in magic angle twisted Ballet graphene and many other systems. In fact, this is a little bit old. By now there are many more groups actually that have done this. Now, the next thing that happened also is that plenty of other phenomenology characteristic of strongly correlated materials or quantum materials have been observed. For example, a strange metal behavior, which is one of the strangest phases of the phase diagram of the high-temperature couplet superconductors. Nematicity, Fermi-Surfer constructions, cascades of phase transitions, pseudo-gap physics, all kinds of things, behaviors. As I mentioned, also in this, all phases in quantum matter that have been observed in these systems. We have discovered many other correlated systems. For example, ABC, in terms of pairs of layers, ABC trilayer graphene aligned to HBN, magic angle twisted bilayer graphene. This is two sheets of graphene at 0 degrees, two sheets at 0 degrees, and then you twist it one pair with respect to the other. Okay, so this is twisted by, we call it. Then Moiré transition metal dichalcogenides, etc. By now there are maybe 20 or 30 systems, Moiré systems that the community is investigating very actively and that exhibit all these correlations in topological physics. A very important discovery was the discovery of ferromagnetism, anomalous Hall, and the integer and fractional quantum anomalous Hall effects in the systems, because that brought the role of topology front and center to this field. As I mentioned yesterday, one of the things that makes me happiest is the fact that in this field of Moiré quantum matter, it has meant the merging of several condensed matter communities that didn't interact that closely in the past. On one hand, you have people that did vanilla, graphene, and other two-dimensional material systems, like myself, people that work on strongly correlated materials like the cuprates, the pnictides, the heavy fermions, organics, and people that did topological condensed matter physics, like integer and fractional quantum Hall effects, topological insulators, Wahl semi-metals. All of these three communities come together in this field of Moiré quantum matter because these aspects all appear in the systems. In 2019, together with my friend and collaborator, Senthil, we predicted that various types of, more heterostructures would exhibit nearly flat churn bands. Okay, so they would exhibit topological properties, very unique. And there was also related theory work on the topological structure of, the electronic bands in magic angle twisted bilayer graphene. And just a few months later, the group of David Haber-Gordon published in Science the discovery of magnetism, a special type of magnetism, not related to spin, but orbital magnetism, and a large anomalous Hall effect. So strong Hall effect at zero magnetic field. In magic angle, this was magic angle twisted bilayer graphene aligned to hexagonal boron nitride. We take twisted bilayer graphene and you align it to hexagonal boron nitride, you break asymmetry of the system. Because now the boron and nitrogen atoms break the symmetry between the carbon atoms, and you can realize this effect, okay? This was the first discovery, and just a few months later, the group of Andrea Young at University of California, Santa Barbara, they measured the actually quantized anomalous Hall effect. So not just a strong Hall effect, but the actual quantization, integer quantum Hall effect at zero magnetic field in these systems, okay? The thing got even better when, just 2 years ago, the community realized the fractional quantum anomalous Hall effect. So the fractional quantum Hall effect at zero magnetic field, okay? In two different Moiré quantum matter devices. The first one was the group of Chardon Xu and collaborators, where they measured the fractional quantum anomalous Hall effect in twisted bilayer molybdenum ditelluride. This is a twisted transition metal dichalcogenide heterostructure. So here you can see that you measure the Hall resistance, and it's 3/2, so conductance 2/3. So fractional, conductance at zero magnetic field. Okay, and the following year, my colleague Lon Yu at MIT, he measured, his group measured the fractional quantum anomalous Hall effect in a different Moiré heterostructure. It's called rhombohedral graphene without twist angle, but particular stacking, of the graphene layers aligned to hexagonal boron nitride to make a Moiré pattern, okay? And then measure other different fractions. This is something that, has been, even a tremendous booster to this whole thing, it's an entirely new phase of matter that was not, seen ever before. Okay? It was theoretically predicted. There were many, there were predictions back, 15 years ago or so about fractional churn insulators, which means systems that would exhibit the fractional quantum anomalous Hall effect. But there were theoretical predictions in the abstract, like who knows how, where. There was no concrete system where people thought they might be realized. And then in 2018, no, sorry, not this paper, some theory paper, I don't know if the theory papers are here, but very quickly after our predictions of quantum anomalous, integer. And actually, in that same paper, we also did the fractional churn insulators. But the community very quickly came to, okay, which heterostructure, which angles, and so on, you would need in order to get the type of flat band that will give you a fractional churn insulator and fractional quantum anomalous Hall effect at zero magnetic field. Despite theory coming quickly and saying, oh, do this, I think experimentalists were like, well, we'll see, theories say that we should do this, but most of the time, it's, condensed matter systems are very complex, it's rare that. But very quickly, this was realized, okay? And people were stunned, I remember my colleague, Patrick Lee, told me that I didn't think, he's 70 years old, and he's in good health, and he said, I didn't think I was going to see this in my lifetime, this fractional quantum anomalous Hall effect, magnetic field. So very good work, both by Chardon Xu, also Yishan and Kim Fai Mak, and my colleague, Lon Yu. Okay, so because these are two-dimensional systems, they are readily available for you to explore with local scanning probes. And all, scanning probe techniques have been applied to the system pretty much, okay? Scanning in tandem microscopy, scanning nanosquid, scanning single electron transistor, scanning optical microscopy, scanning transmission electron microscopy, etc. They have been looked at in detail, and you can look at the Moiré patterns and the disorder and everything with all these techniques. And even a new technique has been invented, the quantum twisting microscope, or the scanning quantum twisting microscope, okay? Let me show you two highlights, there's a lot of work. Let me just show you two highlights, okay, of high resolution STM and of this quantum twisting microscope. So first one is this high resolution scanning tandem microscopy. There were very quickly after the discovery, people looked at these things with STM, and they saw very interesting Moray patterns. One of the nicest papers, 2 years ago, is this work by the group of Ali Yazdani, where they look at with STM, so here is scanning tandem microscopy images. You're looking at the Moray pattern. These are the AA sites. So they look over this large area, large by STM standards, and they image these Moray patterns, but they took these images with atomic scale resolution. So that if you zoom in, there is the actual carbon lattice. Okay, and it turns out, that the type of, the different types of correlated insulator states that you can have, in theory, the theories have predicted, many types of potential possible correlated insulator states that you could have at these 2 holes or 2 electrons per Moray unit cell. They all have different imprint in the wave functions at the local scale. Okay, so you have this type of images where you see these bright spots in the AA regions, because, remember, there's high density of state in those regions that electrons like to be. But then if you look locally at the atomic scale, the wave functions look differently depending on the type of many-body state that you have in the system. And they were able to image those wave functions, and tell us which type of many-body correlated insulator state is there, depending on various parameters, such as, for example, strain, etc. Okay? So this is a tremendous tour de force, which has constrained a lot the type of correlated insulator states that theorists, have proposed. Then the group of Shahal Ilani has looked at, invented this technique, the quantum twisting microscope. This is a technique where you have, in this twisted bilayer structure, rather than having the 2 things like this, you have one graphene sheet on a substrate, and the other graphene sheet, you place it on an atomic force microscope tip that you can bring now to the other graphene sheet and rotate in situ. So now we're able, or they are able, to control the relative twist angle between these 2 crystalline structures, but in situ. In my devices, it's fixed. I can choose any angle, but it's fixed once I make the device. In this type of technique, you can actually rotate it in situ and look at the properties, electronic properties of the material as you rotate it in situ electronically. Okay, so this has given a tremendous boost also to the field that many groups, are working on this quantum twisting microscope. So let me just, end this section by saying that, why stop at 2? You can put 3, 4, 5 layers, on top of each other, and angles and so on, and the theories are predicting all the magic angles with all the different number of layers and so on. So we call this Moray Magic 3.0 and beyond. So in my group, and also in the group of Philip Kim, a few years ago, we discovered tunable strongly correlated superconductivity in magic angle twisted tri-layer graphene, okay, where you have 3 layers twisted, the magic angle is different. And the following year, 3 groups, including my group, we discovered that also magic angle tetralayer and magic angle pentalayer graphene, again, with different magic angles, for each condition, is also a superconductor. So we have now that this magic angle multilayer family is a robust family of Moray superconductors. It's just it's not just twisted bilayer graphene, it's actually a family of superconductors, with different layers and so on. All right, I'm gonna go quickly through this, the magic of electricity in bilayer boron nitride. So all of these behaviors that we have seen, one of those that was absent initially was this ferroelectricity, which is a very characteristic, phase of condensed matter. And that is because in general, order doesn't like 2 dimensions, okay? I mentioned yesterday there is this theorem that forbids that graphene exists. The same theorem forbids that magnetism, that superconductivity, that ferroelectricity exists in 2 dimensions. Okay? And in fact, if you take 2-dimensional ferroelectrics, there are only a handful of them. Most ferroelectric material, to make them thin towards 2 dimensions, and ferroelectricity disappears. Okay? But this is not what I mean by 2-dimensional ferroelectrics in what I'm going to tell you next. These are all materials which are strong ferroelectrics, and they still survive when you make them very thin because they're very strong or because of some particular accident. What I'm going to tell you about is about making a ferroelectric out of non-ferroelectric component. In the same way we made a superconductor out of non-superconducting component, because graphene is not a superconductor. Okay, so for that we can use bilayer boron nitride. Okay, so boron nitride is this boron and alternating nitrogen atoms. The usual stacking when you grow a crystal of boron nitride is this AA prime stacking, which means boron and nitrogen atoms alternate in the z direction. They're exactly on top of each other and then alternate in the z direction, okay? That also means that, layer number 2 of boron nitride for bilayer boron nitride is rotated 180 degrees on top of layer number 1. That's how crystals grow, okay, like this. Since we can put, two the materials on top of each other with any angle that we want, we can actually do the following. We can take a monolayer of HBN, single layer, 1 atom thick, and we can cut it and place it on top of itself at 0 degrees instead of 180 degrees as the natural crystal wants to, okay? So this is called parallel stacked bilayer boron nitride. So we have 0 degrees, layer 2 on top of layer 1. This is something very uncomfortable. Boron doesn't want to be on top of boron and nitrogen on top of nitrogen. So what the system does is it shifts into one of two configurations, either a AB stacking configuration where the boron sits on top of the nitrogen, or a B stacking configuration where the nitrogen sits on top of boron. And it turns out these two configurations have electric dipole moments which are opposite to each other. So if you have a way of switching between these two, you have a switchable ferroelectric, something with an electric dipole moment that you can switch, okay? And indeed, that's what we did, okay? We made devices where we have this parallel stacked bilayer boron nitride. Now, since boron nitride is an insulator, we couldn't measure directly in a transport group. My group is an electronic transport group, the properties. So what we did is we placed graphene on top, and we made something known as a ferroelectric field effect transistor, where we're looking at how graphene conducts based on what is the ferroelectric polarization state of the ferroelectric underneath. Okay? And that gives rise to this resistance versus voltage, where you have this, if you measure in one direction, you have this peak in resistance. Remember, graphene, the conductivity is V-shaped, so resistance, which is 1 over conductivity, is a peak versus density. Okay? So you measure this thing. At some point, the ferroelectric switches, then you go back and you measure this hysteresis. Okay? This was measured not only by us, but by several other groups at the same time. If you do this in a map, this is a dual gate. Now we have 2 gates, so that we can apply a transverse electric field. You can see how this switches abruptly, and then if you reverse the gate voltages, you switch back at a different electric field, so there is a hysteresis, a coercive field. Occasionally, you can catch a domain wall in between your contacts, so you see both peaks for both the DA and the AB domains. This is something that happens for 0 degrees. If you twist a little bit, now you form the type of ABBA domain that you have in magic angle twisted bilayer graphene, except that now they are different. They have opposite electric dipole moments in this Moire pattern, okay? So can we see this actually? Indeed, if you do piezoelectric force microscopy, which measures, the polarization, you can see these patterns, in the phase and amplitude, where you see these Moire patterns with opposite electric field, alternating these Moire structures. Okay? You can put it on top of each other like that. Now, this is something which works at room temperature. It's about the only thing I've done in my life that works at room temperature. So it's actually, I'm pretty proud of it, So this works at room temperature. It acts as a memory. You can cycle it many times, And this was published in 2021. We spent a few years looking at how good could this be as a ferroelectric, okay? So just this past year, we published that this turns out to be among the fastest, might be the fastest, and the most endurance, ferroelectrics in the world. The switching speed is less than a nanosecond. We don't have, equipment in my laboratory and in my colleagues' laboratory, we assure you, to actually check how fast it is. We just know it's faster than a nanosecond. That's already, commercial, grade. And this thing can switch, back and forth, back and forth, back and forth. This thing over 100 billion cycles without degradation. Maybe we just got bored, of switching this thing, after 100 billion times. That's higher than pretty much any other ferroelectric in the world. Okay, and this works all at room temperature. Okay, so the community is getting very interested in this type of, sliding ferroelectricity, a new type of ferroelectrics that we didn't see before. Okay, the same thing you can do. All we needed to do this was this AB sublattice, okay, the symmetries. So we actually, can we do this with other materials? Yes, okay, in particular the transition metal dichalcogenates have the same structure. So within 6 months of the previous results, we realized, ferroelectricity, these are data for Kelvin, but this works at room temperature with all the transition metal dichalcogenate, the most famous one, semiconductor one, okay? So that means that within the span of a few months, we have essentially doubled the number of 2-dimensional ferroelectrics. But of this type, you can get hundreds more because we have hundreds of materials with those bipartite lattices. And in particular, all of these materials, if they have other order, like if they are ferromagnet, or if they are superconductor, or if they are something else, you can engineer ferroelectricity into it. So we can make multiferroids, we can make superconductor ferroelectrics, etc. And these have been, several of these have been demonstrated. Let me just very quickly tell you, we've done all of these phases and using, one or a few type of type of atoms, okay? Carbon, for example. That, so for the students, it's good to think about how come, that with just a single type of atom, you can realize all of these physics matter. So what are the key ingredients that, allow you to do, all of this physics, okay? So think a little bit about that. We have done this with, again, graphene, maybe with HBN, with transition metal chalcogenide, but we have hundreds of two-dimensional materials. Some of these two-dimensional materials by themselves are very exotic, like titanium chloride is a tentative quantum spin liquid, the ferroelectrics and superconductors, which are two-dimensional by themselves. So you can imagine that now a lot of people are calculating, well, let's see what happens if we twist these, what type of other exotic behavior we could get. And two examples are, if you twist high-temperature copper superconductors, Marcel France and colleagues here in Canada have predicted that you would get high-temperature topological superconductivity, okay, beyond a critical angle. And there's some people who are starting to investigate these things. If you take two-dimensional crystalline magnets, okay, and you twist them, you can get something known as moire magnets and moire skyrmions, where you have special spin textures, in your moire patterns, etc. And there are also some experiments in this direction already happening. Beyond that, and this I mentioned yesterday, so I'm going to go very quickly through it. This is all in condensed matter physics electronics that I mentioned about, but you can do this thing with cold atoms. You can do this thing with phonons, okay, slow down the speed of phonons. You can do this with photons, more and twisted photonics, because you can slow down tremendously the speed of light when you twist photonic lattices. You can do more and twisted electrochemistry and catalysis, okay? Because these local regions have very different density of states and catalytic and chemical properties. And some people even think that you can do more gravity and cosmology with some analogs of these structures. So with this, I want to end again with the acknowledgements. This is something that is done with a large group of students and collaborators and a lot of funding and support. And I want to, since I'm here, particularly thank CIFAR, the Canadian Institute for Advanced Research, for making me a fellow and for recently renewing our program, our quantum materials program, so that for the next 5 years, I will continue to visit Canada very frequently. Thank you very much for that.
Okay. Thank you very much for a wonderful talk, Professor Lopera. So now, yeah, I was probably the only person in the room who was kind of nervous about the time, but I was everybody is staying here, and then I think it's I'm assuming that there are a lot of questions. So even though that we are past actually the time, I'll just entertain a few questions and then see what happens. So I guess Eames.
Hello? Okay. You were mentioning the cold atoms experiments, and you were saying that the 1 nanokelvin is actually like a high temperature regime. What's the energy scale that you're comparing to in those experiments?
So, there are different energy scales that you can look at. It can be, the on-site repulsion, for example, that energy scale can be a bit higher, you can look at, various types of exchange, or the hopping energies between the, lattice sites. So this is an order of magnitude, the temperature. My colleagues, at the MIT Center for Cold Atoms tell me that currently their temperatures, that they're looking at is of the order of, between a few hundred picokelvin and a nanokelvin, and they're struggling to go lower in temperature. They think they need to go a factor of 10 or 100 lower to get to that, for example, D-wave superfluidity regime due to repulsive interactions. And attractive interactions they did already back in 2002.
Yeah. Hi, thank you for a great talk. I wanted to ask about the 3.0.0 Moire materials. So you are able to obtain these flat bands. So you were also observing superconductivity, and is it really a case that you were observing superconductivity in higher and higher temperatures as you were like stacking more and more of them? And generally, maybe a broader question, what are differences when you're stacking them? Are there any interesting things that are happening when you're moving to these menu layers?
Very good. Let me try to go to that slide. Yeah. So as you can see here, for bilayer, tri-layer, 4-layer, 5 layers, TC increases, but only by a little bit. Okay. Turns out the magic angles predicted for 2, 3, 4, 5 layers, they are slightly different. Okay, they increase the magic angles, but they increase on this circle, so they reach saturation. Okay, if you're curious, you can check this paper. There is actually something related to the golden ratio, in the way the angles go, which is very interesting. But there is saturation. So the Moiré patterns, the Moiré wavelengths, go to shorter and shorter distances, but they saturate. They saturate like this, right, for infinite layers. So it's not like we get much closer, much stronger interactions and a much higher energy scale by going to a larger number of layers. Okay, TC just increases, but it saturates, to something of the order of 2 point something Kelvin. Okay, so a way to get to room temperature won't be to add more layers, at least within this simple, model for how to generate flat bands as you keep adding layers. Okay. Something that is interesting, I didn't have time to mention, but in a more specialized seminar I would have mentioned, is that this, magic angle twisted bilayer field, in particular the tri-layer, is the strongest known superconductor that exists. What do I mean by that? It has the highest critical temperature compared to the Fermi temperature or the density of electrons that you have in your system. This is an extremely dilute superconductor, 1 electron or 2 every 10 nanometers, right? That's extremely diluted, orders of magnitude, less density of electrons than a regular superconducting metal. However, the TCs are similar to, for example, aluminum, or higher than aluminum, which has 4 orders of magnitude larger electron density. So we do not understand exactly how come that the pairing glue of the Cooper pairs in magic angle graphene is so strong. If you had the same pairing glue strength of the Cooper pairs in regular metals, or even in the high temperature Cooper superconductors, you would have well above room temperature superconductivity. Okay. So this is something that if we understand exactly what are the key ingredients, is it the flat bands? Is it the topological properties? Is it the quantum geometry, which is something now the theorists are exploring? If we understand exactly how come that the pairing glue is so strong, we may be able to implement some sort of design principles at regular atomic scales lengths, and Fermi temperatures that would give us ultra high temperature superconductivity. Okay, but that is a big if. We don't know yet. We first have to understand it and then see if those same ingredients can be implemented at smaller, at regular, Fermi temperatures of metals.
Okay. Okay. So the last question.
Hi, I was just wondering about the asymmetry of particle and hole doping in the bilayer system. I'm used to cuprates where, you're using, as you said, different atoms when you're doing the different dopants. So I was wondering if there's anything to do with, because you're just varying the gate voltage, right? So is there any reason for that asymmetry?
Very good. So the short answer is we don't know, but there are things that are already breaking the symmetry naturally. The electronic structure in the simplest model is symmetric, electron hole symmetric. But actually, when you do a bit more refined models of the electronic structure, already the electronic structure is not symmetric. Okay, so that would give you already a natural symmetry. However, the symmetry is very strong, so it's not very clear if that is enough, to give you the degree of asymmetry that we see. As you mentioned in the cuprates, it's very asymmetric, and yes, you're using different families, but it's not clear, to the cuprates community that that is the original difference. Some people think that the behavior of holes is very different from the behavior of electrons. Okay? So we do not have yet a good theory for why the degree of asymmetry. What is seen at the integer number of electrons or holes, 2 electrons or 2 holes, what has been experimentally measured is a phase transition. In fact, there's several for each integer number of electrons or holes per Moiré unit cell. So we call it a cascade of phase transitions. So that thing happens in a phase transition. And the strength of the phase transitions is different for electrons overall and for holes overall, okay? So there are multiple ingredients there, and the community is still trying to figure out, what is the asymmetry difference.
Okay, with that, let's thank Professor Hero again. Okay, so I just want to remind you that the next Welsh lecture will resume in this room at 2 o'clock. So after lunch, we'll meet you again here. Thank you.